Okay, other indeterminate forms. Limits of the form 0 times infinity and infinity minus infinity are also indeterminate. To evaluate limits of these forms, we must first strike the original limit to an equivalent limit, but in the form 0 over 0, infinity or infinity, and then use L'Hopital's rule. The reason why these things are indeterminate is that, infinity is not a number. Infinity is the concept of growing without bound. And so when we're talking about infinity minus infinity, it matters which one is getting bigger faster, which one's approaching infinity faster. Is this approaching infinity so much faster that, it just overwhelms the whole thing? Or are these things, is this infinity always twice as fast as the second infinity? It matters how fast these things are going. And the same thing with the 0 times infinity. It's sort of a power play. Which one has more influence? Is this one coming closer to 0 so much faster that it overwhelms the infinity? Or the other way around? Is this one going towards infinity so fast that it overwhelms the 0? And so that's why they're indeterminate. And then what L'Hopital is doing for you when it takes the derivative, remember derivatives give you rates of change. It really then is looking at how fast. Remember when we talked about derivatives way back when, we said how fast? That was rate of change, that was speed, that was velocity. When we take the derivative, it is then actually comparing the rates of these things and comparing that to see if we get a limit. But 0 times infinity, infinity minus infinity, as limits are indeterminate. And the only hint we get is when we have 0 times 0 or infinity minus infinity, you got to rewrite the original guy somehow so that it's in the form 0 over 0 or infinity over infinity. So let's look at this guy first. Try substitution. And so that's going to be 1 over 0 as from the right minus 1 over sine 0. That's going to be 1 over 0 from the right minus 1 over 0. And that would be 0 from the right as well. We're not going to really fuss with that too much. But that gives me infinity minus infinity with horrible, horrible notation there, but that's okay. So we have infinity minus infinity, that's indeterminate. And so what I have to do first is I have to rewrite to either 0 over 0 or infinity over infinity. But in other words, rewrite to one fraction. So let's do that. My best hope for getting a fraction, get a common denominator, combine those guys. So my common denominator is going to be x sine x. So we have 1 over x times sine x over sine x minus 1 over sine x times x over sine x, which is going to give me limit as x goes to 0 from the right of sine x over x sine x minus x over x sine x, showing every step I can think of. And so I have sine x minus x over x sine x. Let's check the form. So that's going to be sine of 0 minus 0 over 0 sine 0. That's 0 minus 0 over 0 times 0, 0 over 0. I can now use L'Hopital's. So doing some algebra was able to change the original form now into a L'Hopital form. Use LH. So doing that, that's going to be the limit as x goes to 0 from the right. Oh, derivative of sine is cosine. Derivative of x is 1. Product rule on the bottom, plane first. Derivative of the second, plane second. Derivative of the first. Just going to clean that up a little bit. So we've got cosine x minus 1 over x cosine x sine x. Substitute, see what we get. So that's cosine 0 minus 1, 0, cosine of 0, plus sine 0. That's 1 minus 1 over 0 times 1 plus 0, 0 over 0, which just tells me to use L'Hopital again. As long as you still have 0 over 0 or infinity over infinity, you can use L'Hopital. So we will do it again. LH. This is supposed to be from the right. Okay, doing the derivative of my numerator. Derivative of cosine is minus sine. Derivative of 1 is 0. Product rule right there. So doing a product rule now. Plane first, derivative second, plane second, derivative first, and then the derivative sine is cosine. So all of this is a product rule on x cosine x. Cleaning this up a little bit, that's negative sine x over negative x sine x plus 2 cosine x. And let's substitute now. So that's negative sine 0, negative 0, sine 0, plus 2 cosine 0, which gives me 0 over 0 times 0 plus 2 times 1, 0 over 2, and 0. And so there was my limit. But the first point of this problem was infinity minus infinity is an indeterminate form. I had to rewrite it to really essentially one fraction and hope that that fraction was either 0 over 0 or infinity over infinity. We had 0 over 0. Then we used L'Hopital's rule. And in this particular case, we had to do L'Hopital's rule twice, but we got the answer. Okay, so this kind of subsection started with that infinity minus infinity and 0 times infinity were indeterminate forms. So let's look at the next problem. Let's check it first. So that's going to be 0 times the natural log of 0 squared. Now let's remember that's essentially what the logarithm curve looked like. And the limit as x goes to 0 from the right of the natural log of x is negative infinity. And if I come from the right, going nearly straight down, negative infinity. So the form I have here, horrible, horrible notation, 0 times infinity. So it's indeterminate. My only hint here is to rewrite to 0 over 0 or infinity over infinity, because that's the only thing L'Hopital's works on. Now there is a standard technique for these guys. Which is going to work for the things that we do in this class. You're going to take one of the factors. So in this case, either x or natural log of x quantity squared. You're going to take one of the factors, form its reciprocal, and put the reciprocal in the denominator. Meaning this. So there's my problem. X times log x quantity squared. Got two factors. I actually got three, but we'll count this as one factor here. I've got x, natural log of x quantity squared. I pick one of the factors. You pick whichever factor you think will be easiest to work with. So I'm thinking about x, I'm thinking about log x squared. I think x is way easier. So I've decided to work with x. So I'm going to leave the log x completely alone, and then I take the factor that I've chosen, the easiest factor, the one you think is going to be easiest to work with, in this case x. Take the factor you've chosen, x, form its reciprocal, which would be 1 over x, and place it in the denominator. That's the standard trick. Now here, work it backwards. Students are like, oh, why can I do that? Note, if we go the other way, and I'm not going to write down the whole limit symbol. That's died. We can undo this very easily. No, we could simplify this back. Because, you know, that's not simplified. It's kind of nasty looking, but it's going to be the form that works for us. Right? Division, fractions are nothing but division, so I can bring that guy up and flip it. And I get back to what I had. And so that's why I can do what I did here. All I sort of did was unsimplify it. That's what we really could call this. We unsimplified this expression, because if we simplified it, we'd go this way and get that. So I unsimplified it. But the reason why I did this, my form now will be log of 0 squared, 1 over 0, which would be infinity over infinity, and now it has a L'Hopital's format. So when I have 0 times infinity, this is going to be the standard technique. Take one of the factors, form its reciprocal, and you take whichever factor's easiest to work with. Clearly in this case, x is the easiest thing to work with in this expression. Take the easiest thing to work with, x, form its reciprocal, 1 over x, and place that in the denominator. And you should then have something that's either infinity over infinity or 0 over 0, as the case may be. And now it's ready for L'Hopital's, which we will do on the next video.